were handled by Rabinowitz. Yeah, the tight, because yeah, right there, the tight case. Right. So the main addition from a dynamical perspective was the over-twisted case where Hellman made use of the classification, Yasha's classification of context structures on S3. But what will be sort of interesting is the techniques that were used there we'll use in the tight case, and we'll try and generalize those. That's sort of the input that we're attempting to do. So related to this, so this question by Seifert sort of showed up in the early 50s, and it took about 25 years before progress started to get made on it. And there's another question that was made in the late 50s, which is there a minimal flow on S3? This is a question due to Gottschalk. And the answer is mostly just big question marks. We don't have much progress on it that I'm aware of. So there's modifications to the problem where progress has been made, but on this specific problem, just really very, very little is known. And it turns out it's a very interesting problem, by which for now I'll just sort of say interesting people, or important people think it's an important problem, and have thought so for quite a while. And you might wonder, like, well, why is it the case that there hasn't been much in the way of progress? And the answer is, well, if you want to show something is minimal, you have to show that you don't have any closed invariant subsets, which are either empty or sort of the total space. So, and the question is, how do you find those? What tools are you going to use? Because the reality is that closed invariant subsets in general can be exceedingly complicated, right? They can be just disaster Hausdorff. You know, they can have sort of fractional Hausdorff measure. They can have a Cantor-like structure, Cantor set type structures. So they're just really bad. And the question is, how are you going to have any tools which are possibly going to find these? So, right. So that's just sort of. Unless, of course, one has a clever idea constructs a vector field for which every orbit is dense. Right. But then still, you need to check somehow that every orbit is dense. Like by construction. Okay. So that's another direction you could go. Obviously, that doesn't exist. Then you actually need an existence result for closed invariant. Yeah. Exactly. Yeah. Right. So now what I want to do is return to the rate case. And in particular, we're going to focus on tight S3. In this case here, right, there exists this, the contact form on S3 can be induced from an embedding of S3 into R4, so that the image is transverse to the radial Liouville vector field. That's how you get the corresponding contact form on S3. And then you do something which is fairly standard if you were raised on symplectic field theory, right, which is this idea to stretch the neck. So what we want to do is, so let's see. So for me, this is going to be CP2, and here we're going to have this CP1 at infinity. And then, as it turns out, okay, so I guess I can draw this right here. This will be our embedded S3 sitting inside there. And we had this result. Well, we had this result. So Gromov proved this result in 1985. That says, okay, if you put the Fubini study metric on CP2, and if you use that to tame any almost complex structure on CP2, then there exists a unique degree 1 embedded pseudo-holomorphic sphere, which passes through any 2 points you might like. So you sort of get a foliation of CP2 away from the CP1, where you have this one point where all your leaves intersect. And the interesting thing then is that you can do this next stretching construction, where we take a neighborhood of this S3 and we stretch it, we make it very long. We still have our CP1 up here, and we make all these conditions on our almost complex structure. We had conditions like, let's see, the J applied to the vertical direction is the ray vector field, and we want the J to be translation invariant in this region here. We can define C to be equal to the kernel of lambda, which is our contact form, and we want J to map the C to itself, and we want it to be the case that if we look at D lambda restricted to C, then this 2 form here becomes positive, definite, or tensor rather, and symmetric. So I think these are all our conditions. And then at the end of this process, right, so the idea is we take this region, we stretch it open. Oops, let's go down further. And so the end of this process you have, for instance, let's try and draw this. I'll have a picture which makes sense if you've seen the stuff before, and maybe not much sense if you haven't. But the idea is that you now have some pseudo-holomorphic curves, then which have some negative end down here, I suppose I should say. Pseudo-holomorphic curves are mapped from a Riemann surface into, well, in this case here, well, we just sort of say an almost complex manifold, so that it intertwines the almost complex structure on domain and target. So you look at the image of these, and you end up with pictures which sort of look like something like this, maybe. Right? You stretch the neck, you have, and as it turns out, for any one of the almost complex structures that you put on this case, you can sort of squish this region down here together, embed it back into CP2, and the corresponding push forward of the almost complex structure will still be omega tame, and therefore Gromov's result applies, so that in this picture here, as you stretch the neck, you still end up with these sort of curves which have to sort of run through this region. And then you fully stretch the neck, and you get something which I'm trying to draw out a little bit more here, where you have some pseudo-holomorphic curves which sort of intersect some component which in the top, some component of a pseudo-holomorphic curve, the topmost piece, which has a negative end, and then we have, in this region here, we have R cross, in this case S3, and we have some pseudo-holomorphic cylinder, and then down at the bottom we have another pseudo-holomorphic piece, which is correspondingly asymptotic in the positive direction. And it's asymptotic to sort of the usual orbit cylinders. So I'm sort of going to assume that people are sort of somewhat familiar with this, so I don't need to go over too many details. But what I want to argue is that there's a key feature of the contact case, right, which is the case that we're sort of describing at this point here, which is that we have automatic energy bounds. So in the HWZ language, there's a definition of energy that I don't like, so I'll change it, but it's equivalent. Right, so this is my definition of energy, and I'll describe it somewhat geometrically here in a second. Right, the idea is that as long as you're only considering curves, you say for instance, the Gromov degree 1 spheres, for instance, then this quantity as you stretch the neck will always be bounded uniformly, independent of which curve you pick, and independent of everything else. So this, geometrically, how do I think of this? Just maybe I should mention that Taub sort of thinks of energy on pseudo-holomorphic curves in kind of a similar way. The idea is that you have sort of, you have a positive puncture which is asymptotic to an orbit cylinder, you have a negative puncture which is asymptotic to an orbit cylinder, and then what you do is you pick out this interval here. So we're kind of thinking of, this direction here is M, and this direction here is R. And so what we do is we pick out this interval here. We thicken up a level set. This becomes A naught, comma A naught plus 1 cross M. And then I kind of ask the question, how much? Well, I would say how much area does your curve have in just this region? And as it turns out, if you take this two form and semi-compose with an almost complex structure, you do get a Riemannian metric. And so in fact, this is computing area for you, or rather pullback area. And so what we're asking is that the amount of area in this sort of thickened slice is independent of sort of where you, well, not independent, is bounded from above, uniformly independent of where you put that slice relative to your curve. Good. So then we say, please.
Before you pass the limit, energy is just global energy is chronological, so that's uniformly bounded. But then when you pass the limit, you can only bound it on every.
So what I would say is, if you use Helmut's, I think it's Helmut's definition of energy, then essentially what you're doing is you're saying, let's see, before you stretch very far but not all the way, and then what you're doing is you're sort of pushing it forward into CP1, and then you're just integrating sort of the omega on in CP2, and you're just integrating this omega on some sort of slightly thickened portion. And of course, because the symplectic form evaluates positively on complex lines, you get something which is bounded from above in terms of it's cohomological. The bound from above is cohomological. And what happens is if you use that same formulation, if you use Helmut's same formulation, then that idea sort of carries over essentially just fine. If you use my formulation, you put an extra constant in there, right? You'd say something like there's I want to say.
What he wants to know is, so if you have a symplectic space where it's a topological, like CP2 where it's topologically controlled, now you take that slice, then make it larger, then you can take the symplectic form up to here fixed and up to there as well, and then you can have different ways how to get from there to there, the symplectic form in one way. In particular, you go very flat, and then have a bump here. And wherever you put that bump, you get that as
yeah.
So you estimate it, actually, the right way to do it is you study this J-homomorphic curve with essentially a large family of different symplectic structures, which outside the structure are fixed, but inside you take all kinds of different things.
Yeah, that can be done. I don't like any of this approach, though. So for me, of course, as I started working on the analysis here, what's most important to me is that I have a fixed metric, and I want my metric to be translation invariant, for instance, right? That's going to allow me to do a certain amount of analysis. And so from that perspective, it makes way more sense for me to take a definition like this as energy, right? Because everything I do is relative to that Riemannian metric that you get, which is sort of automatic once you have your contact form or your stable or even your frame Hamiltonian manifold together with an almost complex structure. It kind of comes for free. And so my attitude was like, okay, let's just make use of this from sort of square one and try and step away from sort of the symplectic perspective, because staying in the sort of symplectic frame of mind here, I think it just disaster happens pretty quickly, and so you kind of have to step away from that, or at least that's what I found helpful. That's how we make progress.
But, so I think in Gromov start, it seems to be that omega is an important thing, and then you take the J, it's an auxiliary structure. But I think when you start studying contact cloud, you should actually make the J, you find a lot of different symplectic structures which are compatible with it, and which form an R vector. So you have an R vector of symplectic structures controlling the intuitively chosen J. So that's a chip. That's a chip that we can go further.
So again, just to sort of reiterate, you've got CP1. As long as you have an omega-tamed, almost complex structure, you have this sort of near foliation by pseudo-holomorphic embedded spheres, the only singular point at infinity where it's not a foliation. And then you do this next direction construction, which has some translation invariant almost complex structure, suitably adapted. But if you do that, then you can always take this, squish it into here, and the push forward of your almost complex structure is tame. And so consequently, you get your spheres. You move back in this picture and then stretch all the way, and then see what shows up in the limit. And what shows up in the limit is you have these in the middle region here, for instance, you'll have pseudo-holomorphic curves which have this positive end, and some work then shows that the positive end you have to be asymptotic to an orbit cylinder. You found your periodic orbit and you're done. So this has been around for quite a while, and so now we have a crazy idea. Replace the tight S3 in CP2, so anything sort of star-shaped, with an arbitrary closed hypersurface. Does the same argument work? I mean, in some sense, you might say, well, it seems kind of plausible, right? I mean, maybe we can sort of adjust this thing so we have, again, our almost complex structure, sort of translation invariant. We have to adapt sort of slightly different because instead of having a contact form now, you have a stable framed Hamiltonian structure. So this is a closed 2 form on your hypersurface. It has kernel, and then this is sort of this provides a framing on your kernel. And so this is a 1 form. And so this pair is the sort of gadget that we get instead. And so you might say, well, maybe the same thing, the same idea works. So maybe it works, but then there's reality, which says nope. And let's see. There's a theorem by Ginsburg and Durrell, which says that there exists a proper C2 Hamiltonian on R4, such that H inverse of 0 is diffeomorphic to S3, and it's a regular energy level, and has no periodic orbits. By having no periodic orbits, I mean the associated Hamiltonian flow has no periodic orbits. So, then comes the bad news. No, let's see. Yeah, they explicitly show that there's no periodic orbit. Or explicit enough. Right. Yeah, that's not known.
They claim that every one of the C2 plus alpha, which actually has some E in Hamiltonian, so Hamiltonian C2 Hamiltonian can become alpha.
Yeah, so there's kind of a hidden plus epsilon here. They claim that the techniques that they use should carry over. There should be no obstruction to increasing the regularity slightly. But they don't, I think, presumably because this was sort of good enough, I think, for this case. So we have this idea, maybe we can stretch and find periodic orbits, but we sort of have this example modulo this sort of regularity issue. We have an example of an energy surface which is S3, but has no periodic orbit. So that seems bad. So then the idea is to say, okay, this is the standard, I think, hope for follow-up, which is, well, what goes wrong? We seem to have this nice idea, right? It seems like it should work. We have strong reason to believe that it's not going to work. So why not? So the preliminary answer is that there's instant loss of energy bounce. So what I said, see if I still have it here, is, yeah, here it is. A key feature of the contact case is that you automatically have these energy bounds. Where I've described the energy in this way, in particular, the way I like to think of it is that in some thickened slice, there's a bound on how much area the pseudo-holomorphic curve has in this region, and that bound is independent of where I take that thickened slice, up or down. So what that means then, necessarily, is, as a consequence essentially of this, is that now, as you try and do this next stretching, you lose this bound. You lose an a priori bound on your energy, and that means that as you slide around up and down, there's going to be places where the area of the portion of the curve just blows up and goes to infinity. Now, I think generally speaking in the field, I think this sign is relevant. If you don't have energy bounds, you don't have much of anything. No energy bounds destroys so much of the standard analysis, pretty much everything, right? So, ye who enter here. Yes.
Various circles of hell with Dante.
Dante's Inferno? No? It's a shame. All right. That joke did not play. All right. So. So let me try and give a picture, a description of it, to kind of give some idea of how weird this is. And that's kind of what got me started really thinking was that I just got stuck, right? This idea that, what happens when you lose that energy bound? Like, what's going on? Or what could be going on? So here's sort of the top end, and maybe imagine that you fully stretch the neck, right? And if you do that, you still have the CP1 that's sort of hanging around here, up near infinity. So it's going to foliate out some sort of nice, some nice moduli space over here, singularly foliate here. You're going to have some curves, and then as you progress, like those curves are going to sort of start to dip down into this negative end, right? So what happens? So I'm going to change this a little bit. So if you dip down, so this path here is going to represent something like a sphere. So this is my minimum, and this is sort of my maximum in some appropriate sense, right? And then the idea is that you have some family, and they're going to dip down further and further into this region down here. What happens, maybe? Well, you start thinking about it, and Right? Maybe something like this happens. The squiggliness here, so we see length, so we should think area, and the idea is that in any sort of thickened region here, as you progress through this family, as these curves dip further and further down into this region, it's the case that the length is sort of larger and larger, which we're supposed to think of as the area or the energy getting sort of larger, larger, larger as you might like. So this can happen. And this just looks absolutely disastrous. And so you think, okay, so nothing can be done. And what bothered me most about this picture, I mean, in some sense you think about it, and something like this, in some sense, has to happen. Because we have Ginzburg-Gerell. We imagine it can be sort of souped up to the smooth case. Something like this has to happen, because if it didn't, we'd have a periodic orbit. Okay.
So even that is not clear, right? What's the equivalent of your previous kind of stable Liouville structure, whatever, where you have finite energy, then that means that you converge into some periodic orbit at infinity. Like, if you're not contact type, then it's not even clear what finite energy means, or is it?
So finite energy is erased. But my notion of energy now in this case, so what happens is on any given hypersurface here, you still have an omega, right? Right?
But it's not a product type.
It's not just the two form on the hypersurface.
It's the two form on the hypersurface, yeah. And so the idea is that now you have something called a framed Hamiltonian structure, right? Where lambda wedge omega is a volume form on your hypersurface, right? On your hypersurface, this is a two form with kernel, and then I can make this non-zero in the kernel, and that's going to give me a volume form on M. And so consequently, and then you can still think of this, the kernel of this guy here will still call C. It's not going to be a contact structure anymore, but it's still a two-plane distribution. And then I can make J sort of maps C to C, and I can still require, for instance, that omega restricted to C, that this is again symmetric, positive, definite. And then consequently, on this R invariant region, then I can talk about an energy, which is again this sort of supremum over sort of all shifts of the integral of let's see, A naught comma A naught plus 1, A sort of U inverse applied to this. This is U star dA wedge lambda plus omega. And this two form right here is translation invariant. It evaluates positively on complex J complex lines, and so we just sort of add it up, and I look at this, look at this, and in fact computes area if we look at the corresponding symmetric bilinear form. And so this is sort of a reasonable notion of energy, and this is what blows up. Yeah?
But it only blows up because of the dA wedge lambda.
Yeah, so that's also important. So because this omega arises essentially as, you pull back, so usually we think of it being omega on the whole symplectic space, which you would write little omega, and I want to write just to sort of separate it out capital omega, right? And so we restrict capital omega to a hypersurface, we get little omega, and consequently, yeah, so you can look at just a little omega energy, and that will be bounded. So you think, so that, in fact, that's sort of a really important point, is that you do have these a priori bounds. That's part of the point. Yeah, it's close, and it's also the case that it evaluates non-negatively on J complex lines, and it also sort of fits together with, you can sort of, it fits together with sort of, in some sense it adds up to your capital omega as well.
So it's on contact type, you see that the transversal control to the vector.
Yeah, so the idea here, the way I think about this is, let's see, the way I think about this is C is kind of area, sort of vertical area, right? Symplectization direction maps to the ring, and then the omega term kind of measures sort of horizontal area. So yeah, so in some sense maybe it's actually, so we can actually be really more precise. What happens essentially is if this is the symplectization direction and this is M, then it wraps around in these big sheets. And so what happens is if you look at each individual level set of your pseudo-holomorphic curve, and you think of a movie as you sort of slide up, you have these loops, and the loops get longer and longer and longer and longer, but they do so very, very slowly, very, very slowly. So your corresponding tangent planes to your pseudo-holomorphic curve, they become sort of more and more vertical. It looks like it's sort of wrapping around and around, and this gives you some idea of sort of the best way. In fact, this is the way you lose energy bounds, or what I think of as local area bounds, and that is that if you work in a little region, right, a little ball, a metric ball, say for instance in R cross your hypersurface, the behavior of your curve inside this region is it just sort of, it's little slices, right? Rather than, for instance, inside this little ball, it's something sort of nasty that sort of, just a total disaster. But that has to be proved, right?
Yeah, so the contact type, when you start the stretching construction, you have this metric ball, and you can't just see the final area where it's going. Because the stuff actually you have one ball, there's actually enough to move that ball up. The amount of area in that ball, you want to do. That's exponential growth, even by zero.
Yeah.
So that's what.
Any other questions so far?
But in some sense, though, there's anything that you're saying sort of locally, like I don't know, is it for each energy component intersecting with a little ball has bounded energy?
That's the key. That's one of the major components to the paper, right? Is establishing that in fact is true. Yeah. Before we get there, though, there's something I want to highlight this because there's a couple of key insights into this problem. So I want to tell you the first one, and then the second one is exactly what you alluded to, which is that if you think about sort of how bad, and this is one of the ways I sort of like to think about things. You sort of imagine, how bad could it get, and then try to find the weirdest feature that just doesn't sit right with you, and build off of that. And for me, I said, okay, we know it has to be the case that sort of the energy kind of blows up. What's the weirdest feature about this that I just thought this cannot possibly happen, right? And the weirdest feature for me was to focus on that absolute minimum. Is it the case that if you focus on the absolute minimum as you run down to that end, that the area blows up in a neighborhood of that absolute minimum? Is that possible? And it seems not possible. You imagine, how is it possible for the area to blow up? You say, well, we just sort of said we expect it to be sort of sliding around these sort of slices like this. But if you have these sort of slices, your minimum is down below that. So you say, no, drop down to the minimum. You say, oh, no, I can't do that. Now I have to sort of come in sort of some other path. But if I come in some other path near that minimum, you kind of expect it to be the case that your curve is now sort of mostly horizontal. But if you have a lot of horizontal area, that's controlled by having a priori bounds on this. That can't happen. So it has to then be vertical. But if it's vertical, then you kind of expect it to extend down below the minimum and give you a contradiction. And so this was like the first component, the first idea, I guess, the first step to sort of say, save time a little bit here. So even if the case the omega energy is bounded, so we kind of move outside of the category of just sort of considering curves that are coming from this sort of Gromov type degeneration, the Gromov next stretching type degeneration. If this quantity, if you consider curves more generally, which come down to a minimum, but they can be complicated. Right, they can have genus, they can have multiple positive positive ends in some reasonable sense. And you focus. So this height here, for instance, is A naught, and this height here is A naught plus R. Right? Then there exists some large constant C, such that the integral of mu star dA wedge lambda plus omega is less than C in this region, which is then A naught up to A naught plus R, and then I look at A inverse on this quantity here. Right, so what am I saying?
C depends on R.
So yeah, C depends on R. C depends on R and all the ambient geometry. So that means your J and your lambda, omega, the corresponding